We're going to finish these notes, and then I'm going to give you 1 page of work for the whole 2 weeks. Because as you can see, the next thing on our outline right here is a quiz, because this is the perfect break in the year, in the semester, in the unit. Okay, so what we're looking for, again, when we have no index. Now, usually what's the number that we never write in math class? We almost never write 1, right? It's never an exponent. It's never a coefficient, right? It's never a denominator. We usually don't write 1. And that's a bit of a problem because in this case, the number that we don't write isn't 1 because you can never find one factor of something. Do you understand what I'm saying? You need 2 things to make a factor. So the number that is here that we never write is actually a 2. Does anybody remember what that little number is called? Starts with an I. Yes, you didn't let me finish my joke, Wong. Starts with an I, ends with an X, has ind in the middle of it. Now you say index. Nice, all right. And that index tells me I'm looking for how many factors? 2. So we showed you how to do this right here. You break it all the way down, right? Now, I did also tell you I was going to show you a shortcut that you can do if you know your perfect squares. So don't write down what I'm about to do yet. Look at that question. When I say break it down, don't do it, but think in your head what you would do to make the factor tree for 300. Is everybody thinking of that? The few people that care, are they thinking of that? Good. So what most of you probably will do is you'll go 300, and then you'll freeze and not write because you're writing on a piece of crap. You're not. You're writing on paper, and you can keep writing. You're not like me, stuck with this thing. And you'll go 3 and 100, and then you'll go maybe 10 and 10, and then maybe you'll go 5 and 2 and 5 and 2. Maybe. Everybody cool with that? That's probably what you would do. But I want to show you a shortcut that you can use if you know your perfect squares. I'm going to stop right there because this is the square root of 3 times 100, isn't it? Which is the same as the square root of 3 times the square root of 100, correct? What's the square root of 100? 10. So this has a group of 2 factors, doesn't it? So if I ever find a perfect square in my factor tree, I can stop there because I know that that number has a square root and it's 10. So I will end up with 10 root 3. Does everybody see that? Here is what it looks like if you do it the long way. 10 and 10, 2 and 5, 2 and 5. So what I have is the square root of 2 squared, 2 2's, times 5 squared, 2 5's, times 3, right? There's a group of 2, so out comes a 2. There's a group of 2, so out comes a 5. Since they're both coefficients, what math do coefficients do? Multiply. So 2 times 5 is outside, and we left the 3 under there. 2 times 5 is 10, and there we have the same answer. One way is significantly shorter. So if you get to a perfect square anywhere in your factor tree, that branch can end. Does everybody understand? So let's put that into practice, because with the next 2, you're going to see how much quicker it can be. If you were making a factor tree for 63, I'm betting that most of you will go 9 and 7. Yes, of course. Right? Would most of you choose 9 and 7? Okay. I can stop there because 9 has a square root, doesn't it? So this is really the square root of 9 times 7. What's the square root of 9? 3. So out comes 3, and we leave 7 under there. Somebody say it. Thank you. That's the whole plan. Oh, good. Bonus point. Go get a gummy bear. And everybody I owe gummy bear. Oh, no, it's none of you guys. It's the other class. They're in the freezer where the gummy bears always are. Just take one, not the box. That's what I said. A green one, good choice. I don't really like green. I know, right? It's weird. Everybody loves green.
Which one is your favorite?
The yellow and the one that should be white but isn't really white. You know that one? Yeah, I mean, I don't know what color it is. It's beige. I don't know. Whatever. All right. In the States, you can get bulk gummy bears from some stores that have the same shape but are completely different flavors, and they're more see-through. I was angry. I bought a giant bag of them, and I brought them back to the place where the spot on the beach where we were camping and surfing, and everyone's eating the gummy bears. And it's like, these are weird because they're like pineapple flavor and all these crazy flavors. And then I look at it, and there's all these crazy colors in there too, like bright blue. And yeah, no, it was wild. Hey, I'm going to be in Vegas. I'll bring some back. We'll have some exotic gummy bears when I get home. How come I...
No, gummy bears.
Gummy bears? No, they're not my favorite candy. My favorite candy, like, again, genres, right? There's the chocolate-based candy, there's the jelly-based candy, and then there's the chewy-based candy, and then there's the minty-based candy. You follow me? Right? So my favorite candy, like, is tough to say. Like, I love Werther's Original, but they're a hard candy, but they're caramel.
You know what's good? Have you ever had those red sour things from ARC?
Those red, sour things.
Yeah, I know.
No.
Sour sugar.
Oh, yeah, see, I don't like cherry-flavored things. I don't like real cherries, and I don't like cherry-flavored things. I know, it's weird. My kids and my wife love cherry blasters. I don't. Not a fan. Don't like cherry lifesavers either. But when I was a kid, red lifesavers were my favorite. But now I don't like them. And then, you know what else is weird? Green lifesavers are my favorite lifesaver, but green gummy bears, I don't like. I don't know. Green lifesavers are the bomb. But I do also plan to go to the M&M store, which are one of my favorite chocolate-based candies. Except I was so happy when they made coconut M&Ms, I almost did a flip in the store. And then I ate one, and they're gross. And then I read the ingredients, there's no coconut in them. Not one. I do like turtles, but I really like the coconut turtles. The ones with the blue. I know.
You like Mars bars?
No, I don't like Mars bars, but I like Mars bars with almonds. But a regular Mars bar, too much nougat. Nougat. I don't like it. And I also don't like Three Musketeers because they're just a Mars bar without caramel. Nougat is that foamy stuff that's in the middle of Mars bars and Milky Ways and Three Musketeers, and it's peanut butter nougat in a Snickers bar, which I do like. I cannot stand Big Turk. My best friend in the world, he's dead now, but he was a big fan of Big Turks.
Have you had a lion bar?
A which?
Lion bar.
No. Let's do math. So, 32. Does it have a perfect square in it somewhere? Yeah, 16 times 2, right? What's the square root of 16? 4. So out comes a 4, in stays a 2. Right? Everybody picking up what I'm putting down? Okay. What about 363? What can I automatically divide 363 by? 3. And what does that give me? How many times 3 go into 3? Once. Right? 3. 0, bring down the 6. How many times 3 go into 6? Twice. 6. 0, bring down the 3. How many times 3 go into 1? 3 go into 3. 1. So it's 121 and 3. Can I stop there?
Yeah.
Why?
1 and 11.
Yeah. Huh? That's cool too. That's just takes slightly longer. Hey.
Quick question.
Yep.
What's the name of the Math 11 A&W workbooks? Are they're made by ITC or something?
Yeah. They're called Math 11 Applications and Workplace. I think I have one back there somewhere.
Betty's trying to order something.
Look around and all that crap over there. Check with my housekeeper, Maria. Did you come across Math A&W workbook? Anyways, 121 square root's 11. So what comes out? 11. What stays? 3. Is everybody good? Yeah, that's what they are right there.
They are called MathWorks.
MathWorks, yeah.
So there's an 11.
Yeah, there's an 11.
It's the same one.
Yeah.
It looks like a 10.
Sorry, Harvard.
Yeah, it's the same company though. All right, everybody cool? So that is simplifying radicals. And what that means is you take an entire radical, which looks like this, and you turn it into a mixed radical, which looks like this. Coefficient out front, something underneath. Everybody cool? We are going to do this a crap ton, this unit, and even more next year, no matter what math you end up in. You got to be able to do this. Okay? Now, this next little bit, I'm only doing this to reinforce what we just did. Okay? So, gentlemen, shut it. Now I want an entire radical. What does an entire radical look like? That. There is nothing out front. So in this question, I have a 2 out front, yes? Now if there is 1, 2 out front, and what should my index here be? It's not written, but what is it really? 2. If there is 1, 2 out front, that means there were how many 2's originally in there? 2 of them. So it's actually the square root of 5 times 2 squared, which is the square root of 5 times 4, which is the square root of 20. Does everybody understand that? Now look at the little shortcut. There was a 2 out front, and the index was a 2. What went back under there? 2 squared. Everybody cool? So what's going back under here? 29's already there. What's going there? 7 squared, which is 49 times 29, which is a giant number. Whatever it is. You'd have to use your calculator. There's one. $1,421. Everybody cool? So what's this one going to be? This one's tricky. Yo. It would be the square root of 144 as an entire radical, right? That's one thing we're doing. Now, because I asked for an entire radical, would you ever write that as 12? If I ask the question this way. No. Right? I know. But you wouldn't, would you? Because I wanted the radical. I am checking to see that you make sure how the mechanics of radicals work. Does everybody understand? But if we were doing math with this question, we would want to use it as 12. Does everybody understand the difference here? 1, I'm asking you to understand how radicals work. That's the yellow. And the green would be what we would do with this expression if we were doing more math. Does everybody understand that? Okay. I want you to try D, because there's a little trick in D that makes things slightly different. I want to see if you can figure it out. You know how to deal with D, believe me. Take a second and try it. So, who has an answer for me? Pardon me? Root 300 with a negative in front. Perfect. Absolutely right. Because is that negative part of what came out from under there? No, it can't be, because you can't bring a negative out from under there in a square root situation. Everybody understand? Just like in exponents. Right? There's no bracket. Good? Okay, now, number 3 is asking you to do exactly what we just did 2 pages ago. You're making factor trees, but notice I've done something a little bit weird to you. What have I done in A and in C and in D that is a little bit weird? What are those things called? Starts with an I, ends with an X, has ND in the middle of it. Index. And what does the index number tell you? How many factors you're looking for, right? So in this first one, we're looking for groups of how much? 3. In the second one, we're looking for groups of 3. In the third one, we're looking for
4.
Groups of 4. Everybody understand? Does anything else change? No. So if you do the factor trees and you find your groups of 2, 3, or 4, you'll be fine, correct? Now remember the shortcut. If you're doing a square root and your factor tree gets to a perfect square, you can stop, right? What if you're doing a cube root? If you get to a perfect cube, you could stop. What if you're doing a 4th root? Same thing, but very few people have their 4th roots memorized. Nerdy math guys do. So, you know, there's only one true nerdy math guy in this room. I accept that. Okay? You guys try A right now, and let's make sure you're doing it right. I'll give you a hint. A will allow you to stop your factor tree before you get to the end if you know what you're doing. Would anybody like to describe their factor tree? Or I'm more than willing to bring you the computer and you can actually draw your factor tree.
Oh, yeah.
Yeah? Here you go, buddy.